Hi, Chem classes. Today we're going to talk about percent composition. And what we'll know is that percent composition, just like any other kind of percent, is a ratio, right? It's a fraction. So it's a ratio of the mass of each of the elements that we have in a compound to the total mass of the compound. So we just want to find out how much of the compound is made up of each of its parts, right? How much of water is made up of hydrogen and how much is made up of oxygen, for example. So we take a typical fraction, a part over a whole, and then we just turn it into a percent by multiplying by 100%. We can get our data to do these types of problems from two sources. One, if we have the chemical formula, we can use that to calculate percent composition, or sometimes we have experimental data to do that as well. So let's look at examples of both of those. Percent composition from a chemical formula requires, of course, that we have a chemical formula. So in some of these problems, you might just be given the chemical formula, or you might even have to look it up or write it yourself, and you'll be asked what the mass is of one or more of the elements in that compound. So in this case, we're talking about the compound caffeine, and we want to know what is the mass of nitrogen, the percent mass of nitrogen in caffeine. So looking at our equation, we're going to need to know the mass of the nitrogen, and we're going to need to know the mass of the caffeine. So if I don't have experimental data for this, where am I going to get this information from? Where do you think I might get it from? That's right, I can go to the periodic table and use molar masses for this information, right? So I'm going to find the molar mass of caffeine. So stop for a second now and find out what is the molar mass of caffeine. So you should have found that there were 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens in caffeine. And when you add up all of their molar masses times the number of atoms there are in the caffeine molecule, you should have ended up with about 194.0 grams per mole. And again, you might be off here or there in a decimal point, which is fine based on the periodic table that you used. All right, now that I have my mass of the caffeine, I can go back to my equation and plug in the values for mass of caffeine. And I also know that the mass of the nitrogen is 4 molar masses of nitrogen, right? Because I have 4 atoms of nitrogen in my caffeine molecule. So in the second step, I'm going to go ahead and plug in my values. So I have 4 nitrogen, so 4 times 14.0 grams per mole, and I just found that my total mass was 194 grams per mole. So I put that in, I multiply by 100, and what do you get? Should have gotten 28.9% nitrogen. So that means caffeine is made up of 28.9% nitrogen. And if we did a similar calculation for the other elements in caffeine, we would have determined their percent compositions as well. So sometimes you might be asked to determine all of them and sometimes just one. Now, the other way that we can do percent composition is if we have actual data, lab data to work with. So let's take a look at this problem. We have a student who's preparing a compound of tungsten chloride. They start with 3.946 grams of tungsten and 3.806 grams of chlorine, and the question is calculate the percent composition. So if it just says calculate the percent composition, what you're being asked to do is find both of the compounds or both of the elements that you have in the compound. In this case, just tungsten and chlorine. So we want the percent of tungsten and we want the percent of chlorine. So take a second, tell me what is going to be your total mass for this calculation. And you should have added the two masses together because law of conservation of mass says we're not going to lose any mass when we put them together. So if we're putting together 3.946 grams of tungsten and 3.806 grams of chlorine, we should end up with 7.752 grams of tungsten chloride. Okay, so let's calculate the percent by mass of the tungsten. So we're going to plug in for tungsten, the mass of tungsten over the mass of our total compound. From the problem, we know that the tungsten was 3.946 grams, and we calculated that the total mass was 7.752 grams. So dividing those and multiplying by 100%, we end up with 50.9%. You give it a try for the chlorine. Okay, so you should have done the same type of calculation, except instead of the mass of the tungsten, we now inserted the mass of the chlorine, and with 3.806 grams over 7.752 grams times 100%, you should have ended up with 49.1%. Little tip here, right? If you're doing all of the elements in a compound, what should they all add up to? That's right. All of them should add up to 100%. Now, again, you might be off in a decimal point or two just based on the masses that you have. But in general, if you're going to do all of the compounds or all of the elements in a compound, you should end up with a total percent of 100% when you're done. So up now, of course, are some practice problems. Get to the practice problems, different types, both from formulas and also from experimental data as well.